In this video, we are going to look at a brand new way of plotting points in a plane. So the way that we are used to plotting points in the plane is by using the Cartesian coordinates. The Cartesian coordinates, otherwise known as our XY coordinate, tells us a direction to go along the x-axis and along the y-axis. And so we can see that from this diagram down here. If we're using x and y coordinates, we can simply say, well, let's walk so far along the x-axis, and then let's walk so far along the y-axis, until we get to a point P. And so we have the coordinates P in terms of the coordinates x, y. Well, there is another way that we can plot points in the plane, and that is using what we call the polar coordinate system. Now, the polar coordinate system, as opposed to the Cartesian coordinate system, doesn't use an x and a y value, but rather uses an angle and a distance. So rather than saying, go so far along the x-axis and then so far along the y-axis, what we could say is, starting at the origin, let's create an angle of theta, and then walk along a line on that angle out a distance of r. So you create an angle and you create a distance r, and you can locate the point P. So the point P, in addition to being identified as XR, the point P can also be identified using R, which will represent the radius, and theta, an angle. And those are what we refer to as the polar coordinates. And this would be the polar coordinate system. Now, we're doing the polar coordinates here on the Cartesian coordinate system. The polar coordinate system has its own graph, which we can look at in Desmos. Desmos can convert to a polar coordinate system or to a Cartesian coordinate system. So make sure that you check that out in Desmos. So the first thing that we want to do here is to create a relationship between the two coordinate systems. So if we take a look at the point P, the point P has an x and a y coordinate. And what we want to do is see how we can relate the polar coordinates r and theta to x and y. Well, first of all, we'll notice that we have here a nice little right triangle. And so the horizontal leg of this right triangle is an x value. The vertical leg is a y value, and then the hypotenuse is the radius, our r value. So we could use the Pythagorean theorem and say that r squared is equal to x squared plus y squared. And there what we have is a relationship that expresses x and y in terms of r, or if you will, r in terms of x and y. Well, another thing that we want to do is, what about theta? Well, theta is the angle of this right triangle, and we know that the tangent of theta would be equal to the y value divided by the x value. That is the opposite side divided by the adjacent side. That's just a basic right triangle trigonometry identity. And there we have theta being related to y and x. And of course, you could say that theta is equal to the arctan of y over x as well. And so these two relationships here are what we're going to use to convert between rectangular coordinates and polar coordinates. So here is the actual rules that we're going to be using right here. Actually, I did the second rules here. R squared is equal to x squared plus y squared, and the tangent of theta is equal to y over x. I will let you take a look at those, give you a second, see if you can figure out where x equals r cosine theta and y equals r sine theta come from. Okay, I probably should have told you, stop the video, see if you can do it, but you can always just stop the video now. So if we go back to our right triangle trigonometry, there's our right triangle. Whoop, there we go. We can see that theta, the sine of theta, would be equal to the opposite side over the hypotenuse, and that the cosine of theta would be equal to the adjacent side over the hypotenuse, and that's essentially where these relationships are coming from. So we say that the sine of theta was equal to the opposite side, which was y over the hypotenuse, and that the cosine of theta is equal to the adjacent side, which is x over the hypotenuse r. And so consequently, we can algebraically rearrange these to say that y is equal to r times the sine of theta, and that x is equal to r times the cosine of theta. All right, let's put this into some use here. So the first example, we want to convert each of the following points into polar coordinates. So start off with the point 1, 1. And so I like to find my r value first. And this is really pretty straightforward. We're just kind of plugging the numbers into the little formula and seeing what we get. So clearly we end up with r is equal to the square root of 2. And then over here, we have the tangent of theta is equal to y over x. So the tangent of theta is equal to 1 over 1. Theta is equal to the arctan of 1. And so we have to remember a little bit of trigonometry. And so theta is equal to pi over 4. Now it's going to be necessary to think of that angle as a reference angle, because what we need to do is we need to establish what quadrant we are working in. That's something I always like to do right off the bat. So going back here, I drew a tiny little sketch, mostly for my own value, and I put the point 1, 1 in there. So the point 1, 1 is in the first quadrant. It's a point right there in the first quadrant. So I know that the angle is going to be a positive angle, less than 90 degrees, and we're going to have a radius. And so pi over 4 fits the bill. Okay, pi over 4 is an angle in the first quadrant. And then, of course, the radius, the square root of 2, would take me out this distance of a square root of 2. So that meets the requirement of being in the first quadrant. This is an angle in the first quadrant with a radius of square root of 2. Okay, in the second example, we have negative 3, 4. And so let's just go right to the triangle first. Because the x value is negative and the y value is positive, I know we're over here in the second quadrant. So once I find my angle, I need to make sure that I have an angle that is in the second quadrant. So first of all, let's find r. So r squared is equal to x squared plus y squared. We end up with r being equal to 5. And then the tangent of theta is y over x. We end up with theta being equal to 2.21. Okay, and this was theta is equal to a negative 0.27, which again we're going to consider to be a reference angle. Now, this is a little bit more obscure. Where exactly is an angle of 2.21? Is this in the quadrant where we need it? Well, if we're thinking of this in terms of radians, remember that the positive x-axis over here is pi radians, and that would be 3.14. Okay, pi is equal to 3.14. So if we're over here, we are at 3.14 radians. Well, this is 2.21 radians, and so that is going to be somewhere in this quadrant, okay? But 2.21 radians is going to be here. That's where I came up with the angle. I'm sorry, the reference angle was a negative 0.927. Subtracting that from 3.14 gives me the 2.21. So again, what I'm doing is I know that the negative x-axis over here is 3.14 radians. I have a reference angle of 0.927, which would be this angle in here. And so then I subtract that from the 3.14 and I get this angle over here, which is approximately 2.21 radians. And so that does put me in the second quadrant, which is where I want to be. The next example, 0.3. Well, let's just plot that right off the bat. 0.3 is right up here on the x-axis. Well, thinking of the unit circle, we know that that's going to be at pi over 2 right off the bat. I don't even need to do any work, but we will. So finding the r value, we end up with an r is equal to 3. And plugging into tangent of theta, we see tangent of theta is y over x, which is 3 over 0, which is undefined. And so that leads me to believe that must be at pi over 2. Okay? And so we end up with theta being equal to pi over 2. And so we have the angle pi over 2 with a radius of 3. And so writing that in as a polar coordinate, we have 3 comma pi over 2. The next one, 5 radical 3 minus 5. Plotting that, we see that that's going to be down in the fourth quadrant. That point is in the fourth quadrant. Plugging our values very carefully into our function, our relationship here, r squared equals x squared plus y squared, we end up with r being equal to 10. And then tangent of theta being y over x. Again, being very careful and simplifying, we end up with a tangent of theta is a negative radical 3 over 3. That means that theta is a negative pi over 6. And again, some of these, it's going to be helpful to know your basic reference angles, especially for 30, 45, 60 degree angles. And knowing that 30 degrees is pi over 6, and recognizing that as being pi over 6, the tangent of pi over 6. Okay, so theta is equal to negative pi over 6 is the reference angle. Well, that would be a negative if we were to go from here in a negative direction, a distance of pi over 6. And so, as an ordered pair, we have the radius is 10 and the angle is negative pi over 6. And that is in the quadrant that we want it to be in. All right, now we're going to go the other way. We are going to convert each of the following points into rectangular coordinates. So we are starting off with a radius and an angle, and so we want to convert them into x and y. And so again, I'm just going to draw myself a little sketch. I know that an angle of pi over 3, which is approximately 60 degrees, is going to be over here in the first quadrant. So I'm looking for a positive x and a positive y value. And so plugging those into a relationship, x equals r cosine of theta, and y equals r sine of theta, we end up with 3 cosine of pi over 3, which is 3 times 1/2, which is 3/2. And likewise, over here, we end up with 3 radical 3 over 2. Both of those are positive, just as we were expecting. And so our x, y coordinates are 3/2 and 3 radical 3 over 2. The next one, our angle, a radius is 2. Our angle is 3 pi over 2. Drawing a little sketch, I know that that's down here at on the negative y-axis. So intuitively, I know that I'm looking for an x value that's going to be 0. And since this has a radius of 2, If I'm going down on 2 places on the x-axis, I can figure that my point's going to be 0, -2, just kind of intuitively. But let's just go through the process just to verify that by plugging into our formulas. And so our cosine of theta, we have 2 times the cosine of 3 pi over 2. The cosine of 3 pi over 2 is 0, times 2 is 0, just like we expected. And over here, y equals our sine of theta. Y is equal to 2 times the sine of 3 pi over 2. Well, the sine of 3 pi over 2 is -1. 2 times -1 is -2, just like we expected. So it's nice to be able to kind of predict some things, to visualize what you are expecting for an answer. And if you don't get that, check your work or check your reasoning. Next, let's see, I haven't used that color. So my radius is 6 and my angle is -5 pi over 6. All right, so if you need to figure out where that is, remember, so this is 0, and if we're going in a negative direction, pi is over here, and so pi would be 6 pi over 6. If we're going in a negative direction, go back. If we're going in a negative direction, that would be -6 pi over 6. So -5 pi over 6 is going to be down here somewhere. We don't need to know exactly where it is. We just need to know what quadrant it's in. So that's what I'm saying here. I'm showing that it's in the 3rd quadrant and it's a negative angle. All right. So that's what I'm expecting. Let's do some plugging in here. And we end up with x is -3 radical 3. And our y value is -3. So once again, you can see that it's going to be useful to know the cosines and the sines of some of the basic angles. When you took trigonometry, you usually had to memorize sine, cosine, and tangent of 30, 45, 60-degree angles, knowing that this is pi over 6, pi over 4, pi over 3, and then knowing the sine, the cosine, and tangent of those. And so if you haven't done that, or if you're not up on that, you're going to want to make sure that you kind of review some of that, because generally speaking, whenever trigonometry is used in a calculus class, it almost always uses those basic angles, just so that we don't have to do a lot of computer or calculator computation. Okay, so there are our coordinates. All right, next thing here is the uniqueness of polar coordinates. Now, some of you may have been thinking, as we're going through doing some of these problems, that there might be more than one way to express an angle. And as it turns out, there is more than one way to express an angle. And so that's what this on the uniqueness of polar coordinates is all about. So you can read through that, and you can read through that in the textbook for a fuller analysis of that. But let's just go through and do a couple of exercises just to see that this is true. So the first point I want to do here, so this is, now these are in polar coordinates. The radius is 2, the angle is pi over 4. And so I can plot that point right here, 2 pi over 4. So verify that that would be a location for 2 pi over 4. Well, as it turns out, there are many different ways that we could represent that. Right? As long as we have, and the reason that there are many different ways that we can do that is because there are many different angles that end at this same spot. Theta is not unique. So as an example, we could have the angle 2, 9 pi over 4. Well, what is 9 pi over 4? 9 pi over 4 is what we get when we go all the way around. That would be 8 pi over 4, and then up another pi over 4. So remember back to your trigonometry, your pre-calculus, that angles, there's an infinite number of angles. We could do 2 and negative 7 pi over 4. In other words, we're doing the same thing, but we're going in a negative direction. This would be a negative 7 pi over 4. Well, we can also do it with a negative radius. Yes, we can actually have a negative radius. So in this particular example, I'm going to the angle 5 pi over 4. Well, the angle 5 pi over 4 is going to be down here, directly opposite that angle up here. And so that obviously is not the same angle, but if I took the radius and I made it negative, then instead of being a point down here, that point is going to shift over to here, a negative radius. This would be a radius of 2. A radius of negative 2 would be going in the opposite direction. So this would be the point negative 2, 5 pi over 4. And likewise, we have negative 2, negative 5 pi over 4, or negative 3 pi over 4. So where's the angle negative 3 pi over 4? Well, the negative 3 pi over 4 would be going over to this point in this direction, but then having a negative radius, instead of being down here, it's going to go up there. Now, that's just 4 different representations of the same angle. So including the original angle, that's representing it 5 different ways. There's actually an infinite number of different ways of representing that angle in polar coordinates. So polar coordinates are not unique. The last thing that I did here was just to show you what the angle was in rectangular coordinates, is I found the x and the y values using our formulas. And so this ends up being the point radical 2, radical 2, radical 2, radical 2. And all of those angles represent that singular point. Now, in rectangular coordinates, we know there's only the one way to represent that angle, radical 2, radical 2. But in polar coordinates, there are an infinite number of ways of doing that. So let's take a quick look at a couple more examples, and I'll let you look at it in more depth on your own. So we have an angle, we have a point with a radius of negative 3 and 2 pi over 3. So 2 pi over 3 is going to be up here because 3 pi over 3 would be at pi. So it's going to be 2/3 of the way there. This would be like 1/3 of the way there, 2/3 of the way there, 3/3 of the way there. And so we're at 2 pi over 3, but we have a negative radius, which means we're going in the opposite direction. All right, so that's one way of representing that angle. Let's look at some other ways of representing that angle. We could represent that angle with a positive radius of 3 and 5 pi over 3. So 5 pi over 3 is going to be all the way around to here. 3 and negative pi over 3 is simply going to be going in a negative direction. Distance of negative pi over 3 and a positive radius of 3 in both cases. And then we've got the cases where we have a negative radius here. So negative 4 pi over 3, that would be going all the way over here and then having a negative radius. And then 3 and negative 7 pi over 3. Well, negative 7 pi over 3, how are we going to do that one? Well, negative 7 pi over 3 looks like it's going to be going all the way around like that. And so with a positive radius of 3. And those are just 4 more representations. There are an infinite number of representations. And then down here, I converted into rectangular coordinates to show you the point 3/2 and negative 3 radical 2. And you can verify that all of these different angles give us that same rectangular point. And another one here. And I'm not going to say as much about this one. I'll let you take a look at this one and verify that this point right here can be, which in rectangular coordinates is -2 radical 2, -2 radical 2, which makes sense because it is down here in the third quadrant. And we have, these are just 4 of many different ways that we could represent that point. So again, I'll let you verify that these 4 points are indeed the same. And that would be it for this video. On the next video, we are going to take up the notion of polar curves.